it's not
okay.
like in the
Is it
real
okay now?
analysis. I think
Yep.
real analysis would be given a system
Okay.
and go and try to build the irrational number system out of that.
Okay.
So it's just like a very basic introduction to analysis, because before you have analysis, you have to rigorously define what are your like numbers you're working with, right?
Mm-hmm.
Okay, so let's firstly try to think. Okay, we have rational numbers. We know how they work. They're very nice, right? There can't be many of them. And then imagine you have like some kind of p that in the square gives you 2, right? So can you prove that no rational number would ever be able to do this? Any like ideas, like immediate ideas?
I mean, I know the answer though. It's the P over Q proof, right?
Yeah. I mean, you can just write it as like say s divided by t, right?
Yeah.
And then what you're gonna do, you'd be like p squared is like s squared divided by c squared. That's what you're gonna do is like s squared is equal to 2t squared. And then this is actually a bit of like number theory, right? So what are you gonna do here? So s is divisible by 2, right?
Right.
That means that s is even. So basically, the way I like to go about this proof is be like, so then let's do s equals to 2s1, right? Because it's even. And then what we're gonna do, we're gonna go and write it as like 4s1 squared equals to 2t squared, and thus you go and cancel 2's, and then 2s1 squared is equal to t squared, right?
Right.
And so what's happening is like we come into a new cycle that's very similar to this one. Then t is even. Then we can write t equals to 2t1, right? And then what we're gonna come up with is 4t1 squared. Oh, wait, yeah. We're gonna cancel it and be like s1 squared is equals to 2t1 squared. Does it look like something? Yeah, it looks.
S1 square looks like that. Yeah.
Yeah, it just looks like this. Okay, so what we just did is that what we found out is that in order for this to hold, this should hold. And this is like if you go and divide s and t by 2, right?
Yeah.
Okay, the problem is the following. At some point, like our divisors of 2 inside of the s or t should just end, right?
Mm-hmm.
So what we're gonna do after that, we're gonna come to contradiction. So basically, at some point, because s and t are finite, they cannot be like infinitely like many times be divisible by 2. And so either we're not going to be able to find such an s1 so that this holds, or we're not be able to find this kind of relation. Okay, so the process halts. So you have this like cycle going on for like a long time, and at some point it just doesn't work here or here. Okay, so it halts. You come to contradiction. That means this is not true. If this is not true, that means that this is not true, and that means that for any rational p, this is not true. Okay? So what it shows us is that our rational number system has holes, like, and I mean very obvious holes like this. And I can come up with like we never, and we can like do the same proof for say whenever we'll be able to find r squared that's equals to like say 3, right? And you can, okay, so this process will work for at least any prime number. And I think a lot of other numbers too. But prime numbers are like, there are infinitely many of them. So like, this already shows how we have infinitely many holes. So that's not good. And what's even worse is that we are actually, would be able to like approximate to those holes very, very, very closely. But we'll never reach those. So how do you show it? Okay, let A be the set of all positive rationals P such that P squared is less than 2, and let B be the set, and I guess you can guess what coming next, of all positive rational, how do we call them? Okay, P, such that P squared is bigger than 2. So essentially what we're doing is in the system that's like very like intuitive to us, we're just trying to find all the numbers that are either bigger than square root of 2 or less than square root of 2. Right? And they should be rational. And we already showed that there is no rational that actually like equals to square root of 2.
Mhm.
Okay, so how about, do you think there would be a largest rational that's like the most closest to 2?
No.
Okay, great. So now we're gonna see why. Okay, so let's imagine we have some q in the A, right? And I can just give the first q, like be just like 1. Like 1 squared less than 2. Great. So 1 is inside of A. If we have at least one q in the A, what we can do is we can go and define this. Q equals to P minus,
I just have one question.
yes.
And first proof. So when you said that, so what we were trying to prove is that square root of 2 is irrational, right?
Mm-hmm.
So we can say that, well, let's assume that let's assume that square root of 2 is rational, and then there exists a P and Q that can be written P over Q squared equals 2,
Mm-hmm.
and P over Q would have to have no common divisors, or what do you call them, because
Yes.
they would just be
Both of
divided
them
out.
are.
I mean, okay, so basically, you can do this.
Yeah.
So you can just define the rational number as divided by 2 and S and C are like co-prime, and so the proof just how it's like.
Yeah, when you say that
like,
they have
yeah,
two is a common.
yeah, they have 2's in common.
Okay.
But like, I mean, you can just do the same even without this condition, and it would still work.
Okay.
Like, why I did this
Why can you generalize it beyond that condition?
What do you mean? Okay, so the reason why I showed this condition specifically when they're not co-prime, because I just wanted you two guys to like see.
Because we get to one point when they are prime.
Yeah,
then
I just wanted you to see, guys, like how this like works in number theory, because it's a common trick in number theory to
okay.
find an infinite process that goes down,
Oh.
and it's like never stoppable. Just like, I know a word in Russian for this technique. I don't know what it's called in English.
Okay.
I don't know if it actually has a name in English. Okay, but thank you for question. That was a good question. Okay, so basically, let's try to do this. For every okay, let's call this P. So if we can find a P in the A, then we are going to show that there always will be a Q that is just a bit bigger than P, but it's still in the A. So let Q be P minus P squared minus 2 divided by P plus 2. And so basically it just equals to 2P2 plus 2 divided by P plus 2. Right. And so what it means is that Q squared minus 2 is equals to 2 P squared minus 2 divided by P plus 2 squared. I'm not gonna go and check all the like algebra here, but I mean you can do it by yourself if you're interested. Basically, I guess the common question is like, how do you even think about that? So the reason why we need this specifically is that what you want to see, that you want to see a bunch of squares because squares are always positive, and then you also want to see at some point some kind of figures when there is P squared minus 2, because this would define our sign. So this is a way of like trying to come up with something like this. It doesn't have to look always like this. Maybe you'll be able to find your own way of like defining Q. The only thing that we're trying to build here is to just build a specific Q based on the P, such that when you go and compute this, it equals to something like this. And if you look at it, we already know that P squared is less than 2. That means that P squared minus 2 is less than 0. So this is negative. This is positive. Then this is negative. So this is less than 0. So that means that Q squared is less than 2. Right? So basically, only knowing stuff about P, we were able to build Q, which is less than 2. That means that it's in the A. But also, if you notice, wait, what am I doing? Yeah, if you actually notice, Q equals to this, and this. Oh, okay. Let me do. I mean, and we can define P. Yeah, and we define P to be positive. thanks for doing that Aya before. And it means that Q is positive, right? And it's also is bigger than P, and it also bigger than P because say this is less than 0, this is negative, this is positive, this is positive, so this is P plus something positive.
Okay. First question: how did we come to the formula P minus P square minus 2 by P plus 2? Is that an arbitrary thing that you take?
Sorry, how do you come to this thing?
Yes.
Yeah, okay, so that's what I was trying to explain earlier. Is that it looks like kind of random, right?
Yes.
But if you analyze it enough, so basically you're just trying to come up with something that would be first positive and bigger than P.
Okay.
And you, the only thing that you know about P is that P squared is less than 2. So, and that P is positive. So you're somehow trying to build like a function that would have something that has P squared minus 2.
Okay.
This would be negative
Yes.
or positive depending on what if P is less than 2.
But
Hey.
P square is less than 2 is what
Yes.
we've defined already.
Yeah, but the thing is that like we also would be able to use the same Q
Right.
then after to prove that there is actually the same function that always finds something that's less than P. Okay, well, hey,
Yeah.
so just to update you on the things. So we're doing Rudin first chapter analysis,
Can you explain?
and so far what we did is we just proved that there is
Why do we get
never
Q
such a rational P
equal
that P
to P
squared is
minus
equals
P
to 2,
P square minus
and you
2
probably
by
know how to do
P
this.
plus
Yeah,
1.
yeah.
Okay.
I don't get why
Okay, and so now what we're doing, I proved you like that A is a set of all positive rational P's, that is P squared is less than 2, and the same one that's like P squared is bigger than 2, and we're trying to build Q such that if the P is in the A, Q is in the A but it's bigger than.
And this textbook is in the.
So if I ask you to
is this reading sent in the chat?
estimate.
No, but I think you can find a free copy.
Okay, alright.
Okay.
I can definitely find it.
What would you do? What would you do?
Yeah, can't leave and stuff. Okay, so basically what we just did is we found a formula for Q, and it works. So Q is bigger than P, but still, but Q squared is still less than 2. So right, and we chose an arbitrary P, and that means that for any random P,
Yeah.
we'll always will be able to find something that's bigger and closer to the square root of 2, right? So we'll be able to make infinitely many chunks of it and always find something that's closer.
Give me an example.
So it
Give me-
means
do it
there
for
is
this and
no
root 3.
upper bound of this that would be contained in set A. There is no maximal element in
Okay. Okay.
A. And the same thing works for the set B. There would be no lower one. We always would be able to go closer and closer to the square root of 2. Is this understandable to this point? Okay, great. Yeah, and please stop me. I know I tend to go a bit faster sometimes, and my pronunciation is not always understandable. So okay. And now what we're gonna do is we're gonna go and see what is the definition of. Wait, do I want to define fields? Yes, I guess I want to define.
Aya,
Yes.
can you actually, so you just did it for root 2, can you do it for root 3? Because I feel like arbitrarily, I understood what you did, but coming up with something on my own, I would not be able to do it. And in that case, I'm just trying to see if, at least, if somebody else did understand and if they could come up with, say, the same thing to find root 3 as a...
Oh, sure. But I guess, okay, how about you
I'm-
guys try to come up with something like that using the 3? Because
Okay.
it would be just the same proof.
Yes, I just think that if, and maybe it's just me, if I'm the only one who didn't understand, then it's fine and I can figure it out later. But if somebody else cannot come up with it, then maybe it's just worthwhile spending some time.
Sure. That's thank you so much. Okay, so what would be the first step in the proof like that? So P is rational, right? So we can write it as
So as already, yeah.
how do you write integers? Okay, so what would be the first step here?
Just substitute it.
Sorry?
First, let's substitute S over 2 and P.
Sure. S squared by T squared is equal to 3.
And then can we assume like s to be like 3 times because it's three times s.
So s squared is 3 times t squared. Okay.
No. I'm not talking about the first proof. I'm talking about the last proof that you showed about estimating root 2 to the closest rational number.
Oh, you were talking about this one.
Okay,
Yes,
okay.
I'm talking about that.
Oh,
I thought
okay,
it was-
sure. This also actually.
This is okay. This is fine. I understand this.
Okay. Does everybody else understand this one?
Yeah.
Okay, good. So, let me just write you as a cheat because I don't remember this on my own. Like, q equals to p minus p squared minus 2.
By p plus 2.
Plus 2. Okay.
Yes, this is for 2. I'm asking what would you
Yeah,
do
yeah.
in the case it is
But
3?
I think that you actually just plug it into 3 here and you get the same.
Would it work? And I'm
Let-
curious.
I mean,
I don't know.
let's try. Because the thing is that we like even showing one hole would be enough for us to understand that this like something is lacking inside.
I
So,
agree, but
but-
understanding
yeah.
if it's one whole, like I don't know if I understand that, and I want to see if
Sure.
I can understand another.
Let's
like-
see. P plus 3 is p squared plus 3p minus p squared minus 3. So this is essentially 3p minus 3 divided by p plus. Oh wait, what am
And
I?
it's flat 3.
What am I doing?
I think the last one is flat
Oh,
3.
yeah, plus
Flat
three.
3, yeah.
Okay. Okay, so this is positive. Good. And then q is positive. And then also because this is less than 3, then this would be a positive thing, then this would be bigger than p. Right?
Yes.
Okay. So that means q is bigger than p.
Yes.
Okay, good. And then if you want to do, oh my god, please don't make me do that. Q squared. Can somebody help me with this? I'm not very good at arithmetics, honestly. Okay, this is like 9
P
p
square.
plus 1 square. And then we want to take minus 3 out of here, so it'd be like minus 3 p plus 3 square. I hate you, Gaurav. 3 square. What am I doing on this Wednesday night? Okay. What is that? Okay, this is like 9 p square plus 18 p
Yeah.
whatever
Plus 9.
plus 9 minus, okay, this would be like
3p squared.
3p square. It would be like 6
6p.
minus 18
Yeah, minus
p. This would be like
minus 18.
27.
27, yeah.
Yeah,
27.
minus 27. And so this
Yeah.
would look like, did I do everything right? Did I? 3. Okay, yeah. Okay, it looks like I did everything right. Okay, so this would be like, you see why I get low scores on my math test, right? Minus 18. So this would be 6 p square minus 3 p plus 3 square. Yeah, as I promised, this works. Just plug in any prime number instead of like 3 or 2 here, and it will work. Like, cause yeah, I think what we just did, you can just do it was like t here. Yeah. So like, and now the would be the same because we didn't actually use any of the properties of 3. So yeah, that would suffice. Okay. So does everybody understand? Like, you don't have to understand how this specifically how to come up with this at this point, but because when we're gonna like do like trainings for like making proofs, we're gonna do a lot of stuff like this, I hope, and so it would mean that at some point you'll get how to come up with stuff like that on your own. Sometimes it actually may look a bit uglier because I mean your solutions are always a bit uglier than in a textbook, but like if they work, they work. So, and I don't think you can actually like, come up with at least another way of like doing it. Okay. So what are we doing now is we want to define what an ordered set is, because we already defined like what are sets in the reading seminar, and I don't want to go over it again. It was pretty boring. Okay, ordered sets. So they have several properties. First, for any x and y in the S as our ordered set, you either have this, this, or this. Right. Okay. This means that the set is ordered, like totally ordered, right? Because essentially our rotation works like, yeah, it's always like this, right? But there are actually sets when it doesn't work like this. Say, can somebody give me an example of something that would not be an ordered set? People from the reading seminar.
Complex numbers.
Complex numbers? What do you mean?
It's not an ordered set.
I mean, you can make up a way of ordering them, I guess. That you can, like, if you, for example, you can like, take their lengths and then order them by lengths. But also that would really depend on what, like, how do you, because ordering doesn't have to be just like smaller or bigger in our sense, right? Say for example, I can order by inclusion. So if I have like set AB, like I would have like empty set, I would have A, and I would have B, and I would have AB, right? And so if I order by inclusion, it would look something like the empty set is in the set A, is in the set B, and this set and this set are both in the sets A and B, right?
Yeah.
So basically, this and this are not comparable. You cannot say they're bigger or less because they just don't like, coincide, right? So this is not an ordered set, right? If I would have something like just A, then everything would go, and this would be an ordered set because I have only two elements and they are ordered by inclusion, right? So it really depends on what do you define as an ordering. Like I can order, like it would actually be mathematically correct even if I can like go and just like order, say, by colors. Like if I can order my shoes by color palette or whatever, there still would be some reasonable way of ordering stuff. So yeah, don't think about ordering only in terms of like bigger, smaller, or something.
So then, by that logic, are you saying that no unordered sets exist?
What do you mean?
Do you say that there are no sets that aren't
No,
unordered?
I just gave you an example of an unordered set, right?
Right. Okay.
Okay. So, but there is a Zermelo's well-ordered theory I was talking about on the last reading seminar, and you weren't there, Gaurav. So shame on you, because I called you personally. Anyway, if x, y, and z are in the S, if x less than y and y less than z, then it follows then x is less than z.
Yeah.
Okay, so this is just being transitive, right? Yeah. So our ordering is transitive.
Yeah.
Okay? Like it doesn't always happen, right? Not with all the orderings. But with this and with inclusion it does happen. You can, if you don't have like something to do on one like Thursday night, you can think about all different examples of when you don't actually have a transitive ordering or something. Okay, and then yeah, actually they have only two properties. This is an ordered set, and of course it should have like all the properties of sets, but we're not gonna talk about this because we talked about it in reading seminaries. So go to reading seminaries if you want to listen about that. Okay, so now what we're gonna do, we're gonna define an upper bound or lower bound, but this will be quite short. Okay, so alpha is an upper bound of E. And then is the first property, and then second property is if there is something that's less than alpha, then the something is not an upper bound of E. Okay, So alpha is defined as LUB, lower upper bound. This is short term used by mathematicians. If first alpha is an upper bound in E, obviously, because like why would it be in list upper bound if it's not an upper bound? So that's reasonable. And the second, if there is something that's less than it, it cannot be an upper bound, right? Because then this wouldn't be a list upper bound. So this definition seems to be reasonable. And you can come up with a symmetrical definition for greatest lower bound, right? Can somebody just like shortly make it up for me based on this? So alpha is a greatest lower bound if
Y less than alpha. Y greater than alpha, y is not the upper bound. Basically, you just flip the sign.
yeah. And alpha is an lower bound of E. Yeah. Okay, great. So now what we're gonna do? We're gonna skip this. And yeah. By the way, you can also call it supremum. Okay, and this will be called infimum. Okay, this is just like a way to define an analysis, but those terms mean the same. So yeah. What we're gonna do next is define fields. I know it's a lot of definitions, but this is the first lecture. First lectures are always like this, and to be honest, like it feels boring until you start doing exercises. And when you do exercises, you pray for having a definition. Because right now I'm doing an exercise, and I need to have a definition for something being in negative power, and I don't have it. So how do I prove something if I don't have a definition? Okay, so fields. Okay, so fields are basically sets which have two operations. And they are usually called addition, and I'll just put it specifically in the brackets, and multiplication, because they are not real addition and multiplication, okay? This is just intuitive names for them. But basically, this can be like any two operations whatsoever, okay? The only thing that they should adhere to is a bunch of like axioms, and so I'll try to write them very shortly. So basically, if there is like x and y and they are in the like field F, then x plus y is in F, and also I guess yeah, and x plus y is equals to y plus x, so it's commutative. Can somebody, while I'm writing, give me commutative, an example of a non-commutative set, just or operation, like anything that just comes to your mind?
A cross B.
Yeah, cross product. Can you? Huh?
A cross B. Yeah. The
Yeah.
same thing.
Can you come up with something that's like would be like acceptable for everybody who doesn't take the class?
Okay.
Matrix.
Okay, division.
Yeah.
Division. A divided by B
Okay,
is not equal to B divided by A, right? So you cannot just like go and flip the sign here, right? And I know at first it's like kind of confusing, but really don't think about it in terms of addition, because otherwise it would confuse you at some point. Because when you do addition, we do it like intuitively. We don't even think of that we are actually using rules, a lot of rules from it, right? So you have to be like, if addition confuses you, make up some like kind of star or whatever so it doesn't confuse you. Like I actually do that. It does help. Okay, so associative. It means x plus y plus z is equals to x plus y plus z.
The brackets
Yeah.
change.
Okay.
Just association. Okay.
Okay. There is some element 0 in the set F, such that for any element x in the F, 0 plus x is equals to x. Okay? So there is some kind of element that's called identity. Like for multiplication, identity is 1. For summation, it's 0. You can come up with identity for any other operations if you want. And there is also like an inverse element. Say for any x in the F, there always exists minus x in the f such that x plus minus x equals to 0. Wait, actually, do you guys know the cantors? Like, what does this mean, this mean, and this
for
mean?
all,
for
you
all,
know, the
yeah,
set
yeah.
exists.
They exist.
Okay, great. Because I forgot to ask you if you actually know them. Okay, so this is for addition, and there is like another one for multiplication. How do I do it in
It's
a
okay.
faster way?
Yeah,
Okay. So xy is in the f, and then xy equals y x,
Can you send me the book?
and then xy
Do you
z
want the other
equals
books?
to x y z,
Can you send me
and then
chapter? Okay.
like 1 is back equals to 0, and 1x is equals to x for any x in the f, and then there is always such an inverse element so that this holds if x is non-zero. Okay, so this are similar to addition, and yeah, hence this is also similar to addition, but there is a certain thing, it should not be equal to 0. Okay, and so there is another axiom that should tell us how do addition and multiplication communicate with each other. Because if we just do axioms about addition and multiplication, how should we know how to use them both together, right? So we have to have axioms for this too. It's called distributive law. So basically x y plus z equals to xy plus xz. And yeah, and I guess this is all. And from all these axioms, you'll be able to prove like usual things, something like, okay, so if you have x plus y equals to x plus z, how do you prove that from this it follows that y equals to z? Any ideas? You have all these axioms I stated. You have to prove that from this follows this.
X plus y equals to x plus z.
Okay,
Okay, x.
Can you just add the inverse of x?
Yeah,
and
yeah.
stuff?
okay, so we'll tell us, let's add the minus x to both of the sides. And this cancels, and you have y equals to z. Okay? Actually, I think most of them are quite intuitive, but the one that everybody for some reason always forgets is like this one, 0x is equals to x. And so if you want to challenge yourself, it's not actually hard. It's just, like the proof goes in a bit different way, so people forget about it. So if you want to challenge yourself, do this for fun. Like, okay, and if you're using any fact that you derived yourself before, check if that fact already uses this one. Because you don't want to go in circles.
Maybe.
When you're proving the same thing, you have to prove because you are proving this. Okay, so basically, these are the fields. Now let's look at what is an ordered field. Ordered field. It's a field is an ordered set. With the following properties. Such that
It's pretty bad.
first, if you have x plus y is less than x plus z, if all of them are in the field and y is less than z, then xy is bigger than 0 if all of them are in the field, and x bigger than 0, y bigger than 0. Okay? So those are the only things you have to know if you want to talk about ordered fields, and then you can prove a bunch of like other stuff from that. Actually, what you're gonna go there and try to do, I guess what would be kind of necessary is like go and try to define the multiplication stuff and like how do you multiply negative and positives, because it's not something you would define yet. So yeah, that will be something you would want to look at. Okay, but now we're gonna go to an actual fun part that I was looking forward to the whole day because I think it's quite beautiful. What we're gonna do is we notice that rational numbers have this problem that they have like holes, and that means we want to build irrational numbers. And the thing is that, well, there are different ways of like doing it, but this one is when you have only rational numbers and you're trying to build irrational numbers based on this rational number system. And I think it's quite beautiful because you're basically building everything out of nothing, right? Okay, so we're divided by different steps. So step 1. Okay, we're gonna have a set R. Okay, and so members of R are sets of Q. Q is just rational numbers, and we're gonna call them cuts. Called cuts. It's me trying to put it out there. Okay, a cut is just any set alpha in the Q with such that first alpha is not empty and alpha is not equals to Q. So it's a proper subset of Q, which is not an empty set. I mean, it looks reasonable. If P is less than alpha and Q is less than P, then Q is in the alpha. So basically, what does it tell you? Say you have specific elements in the alpha that put them on the like usual line we are very used to, and if there is something that's like less than it, it's all in the cut, right? Okay. Yeah, looks interesting. So it basically would mean that the cut goes like infinitely long there on the left. Okay, and then if P is in the alpha, then P less than R for some R in the alpha. And this is interesting because what it tells us that the cut doesn't actually have the maximum element, right? And basically we can think about it in many ways, but I guess the way you can think about it the most is like there is some irrational number here. We don't have irrational numbers here, we didn't build them yet, but you know they exist, right? So there's some kind of hole in here, and beginning from this hole we have like a cut, right? And it approaches this hole like closer and closer, but not quite there, okay? And I just have all the irrational points on this interval going to the minus infinity. But we actually didn't include minus infinity in this system yet, so we don't have it yet. Okay. Okay, so now with letters P, Q, and R, we always would just denote rational numbers, and with alpha, B, and I don't know how you pronounce this, but whatever, it will be cuts. Okay, so basically, when we define it, let's go to the step 2. The step 2 would be something like, let's understand that all the cuts are proper subsets of each other. So, okay, and we're gonna go and order them. So alpha is less than B, beta is if alpha is a proper subset of beta. Okay, so basically, let's understand we actually can do this. What are the properties that we have to have if we want to order something? First is that there is no other way. Like, it's either alpha less than beta, alpha equals to beta, or alpha bigger than beta. Okay, so basically, with inclusion, it does work. Why? Because our subsets are just something from specific irrational point to the infinity. So they would look something like here one, here one, here one. So it's kind of understandable why they're inside of each other, right? Okay. Okay, and then what you can do is you can be like to be more rigorous. You can be like, imagine that there is some kind of thing that's inside of B, not inside of alpha. You build some inequalities, and then you just prove that like that means that B alpha is in the B. Do you want me to show it more rigorously, or you want to just go and read it yourself? Because this is quite obvious, but it would take us our time.
Okay.
Okay, sure.
Okay.
Okay. Then step 3. Can you guys see from here? Okay. Step 3. What we're gonna do is we're gonna prove. This is, I guess, my favorite part. The ordered set R has the LUB property. Okay. So what is an LUB property? Basically, it means if you have some, like, say for example, if you have a set E, and the set E has at least one upper bound, that's in the set S, and S includes E, and there's some kind of an upper bound for it, that means that set E has an LUB, so list upper bound.
That is greater than that.
Oh?
That is greater than the least upper bound in the former set, right?
Yeah, the list upper bound of E, and it's inside of the E.
Okay.
So yeah, this is a very cool property. Not all the sets have it, but whenever a set has it, it means that you can do a lot of cool stuff with it. It means that it makes your life like very, very easy. Okay, how will we do that?
Isn't that just the same as any subsequent set encloses the former set?
Sorry, can you repeat again?
Isn't that the same as saying more formally any greater set, any subsequent set that is further in the ordering encloses the former set?
No.
Why?
Because the thing is that the way you can do it is basically not every set first has an upper bound.
Okay.
So there are like tons of sets that wouldn't just even have an upper bound. But even if they would have an upper bound, you can always maybe you cannot like reach the least upper bound. Say if I have a set, if I have a set, if I have an interval from 2 to 3, right? So basically it means that my point that 3 is not included in the set, right?
Yes.
So that means
There's no defined least upper bound.
wait.
There's no least upper bound.
No, I'm not saying no. Okay, yeah. So if the 3 is included in my set, then it would mean that I would have an upper bound of 4, right? 4 is my upper bound. For any of the elements from here, 4 is bigger than 1, 2, 2.5, and 3, right?
Yes.
But the thing is that like you can go very close to 3. You can be like 3.0000, but it would never have a least upper bound outside of this area.
No, so if we define a set to be given a set has a least upper bound, then we can just say that any subsequent set that is greater than, that is further down the order encloses that set, right? Because it's like 2 to 3 but 3 not included will have a subsequent set which is 2 to 3 included, right?
Oh, so you're just trying to say that you are able to enlarge your stats by
Yes.
including. Okay, yeah,
Is that what the property is?
No, the property because the property you're talking about like making up a new set.
Right.
But the property is you are given 2 sets, E and S. And in this specifically already given set E and S, if there exists an upper bound for E in the S, then E has an LUB. Because I can build my sets E and S in a very random manner, so you will not be able to find a least upper bound, right?
Can you give an example?
Oh my god, I hate when you like put me on the spot like that. Okay. So, and you guys can like help me with finding an example.
Sorry, I'm not understanding. If you are, then just like it's fine. If
No,
everybody is, you guys can.
it's not that you asked
push
a
it
question. It's just I didn't have a specific.
Yeah.
I didn't prepare an example for it, right? So okay. So when do you? Okay. So if I have like 1.9 or lot to 2, so 2 would be my upper bound, right? And I just like throw it out of here, and so it goes.
Then there's no
And so-
LUB.
Yeah, and the thing is that if I go and I do like 2.0, yeah, if I go and I just like make my set all of the like numbers from say 1 to 3, and this would be my set S, but without the number 2. So I just chose number 2 out of my set S, and I define my set E as all the points from 1 to like 2.999, right? Then this are the upper bounds, but there is no this upper bound because like they all would be close and close and close to 2, but they would never reach 2, right?
Okay, you mean like the set 1 is closed and then that one is not closed. The set.
Wait. What is closed?
Okay,
In
so it's the set like 1 to 2 closed. What's
Oh
that
yeah,
set? Set E.
So the set E, yeah, it is like 1, 2, 2, like that.
Oh, okay.
Okay. Thank you for asking.
Can you keep that? Can you keep? Don't erase that. Can you not erase that, please? I want to see what you wrote. I can't.
Oh,
Yes.
sorry. 1,
So it's just
2.
like the set.
He just asked if E is equals to this.
Yes.
Yeah.
What
Okay.
happens when E is closed? In
Yeah.
that case, then
In this case, 2 is an LUB.
yes. Okay.
Okay. So is that understandable?
Mhm.
Okay, everything is crystal clear.
What's the full name of ARUB?
Least
Low
least
star, low
upper
star,
bound.
least upper
Least
bound.
number. Oh.
Okay. So yeah, thank you for asking a lot
Should we
of
write it
questions,
down?
Gaurav. Like I feel like you're contributing a lot to this lecture because you're making it's clear for everybody. Okay. So what we're gonna do is we're gonna try to prove that our set of our cuts has a least upper bound property. So let A be a non-empty subset of R and assume that B is in the R is an upper bound of A. Okay, so everything's clear to this point. Define blah, 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 to be the union of all alpha in the A. Okay, so basically what we're doing is that we have some kind of a subset of R. So it basically means R is our cuts, right? So these are our cuts, and we have like a lot of them. And then we take some kind of like a subset of R's. So like, say I want to take this cut specifically, and I want to take this cut specifically, and put them in my subset R, or A. Okay? And then I assume that B is my upper bound of A. And don't forget that for us, upper bounds in R are by inclusion. That means that B would be something that has both of those cuts in it. It can be in this itself, it can be something here, right? So B is in our upper bound. And then what we're gonna do, we're gonna show that this, how do you call this Greek letter?
Gamma.
Is
Gamma.
it gamma?
Gamma, okay, gamma is the union of all alphas in the A. So basically we take all the elements of our set A and we go and take a union of them. Why do we have to do that? Because A may be infinite, right? Because I can take maybe like a lot of these like cuts that kind of like go and approximate to a very big cut, but I never take this big cut in my set A, right? So the cuts can also approximate each other, okay?
Right.
And so when I take this as a union, I kind of cheat because a union of infinitely like things approximating to something is this something in a way.
Right.
Okay, right? Because unions, they work as limits in analysis, kind of. It's not a very strict definition. Like I'm just giving you an intuitive sense. Because whenever you need something that's kind of like a limit, but you're not quite sure if you're allowed to do that with this sets, go and take a union. Like I swear, when you start doing exercises, you'll know what I mean. Okay, so this means that this is an upper bound, right? Because it's a union, it contains all of it, so it means that it's bigger than all of it. Right, it's an upper bound, the first requirement met. And then let's assume that it's actually, now we just have to prove that if something is less than it, then it's not an upper bound, right? Okay. Let's pick P out of the gamma. Then it means that P is in some kind of an alpha 1, right? And alpha 1 is an 8. So basically what it means, because this is a union, if something is element of a union, that something is an element of some set of the union, right? Okay, nice. So that means that if there is some kind of Q less than P, then Q is in the alpha 1 by the property of our cuts. And then Q is in the gamma 2, right? So basically, if something is here, everything here is in the gamma 2. And then what happens is that if there is some R that's in the alpha 1, and then there is R bigger than P, we see that R is in the gamma. Okay, why? Okay. So basically what it means is that if there is something that's bigger than our chosen element, but it's still in the set, then it's still in this set. Okay, so this is understandable so far. What did I do next? I should have said. Oh no, I'm sorry. I'm doing a stupid thing. So basically, what we need to prove is that because for it's a property of the cut alpha 1 that for any P there always exists R that is bigger than P. That means that for any P that we chose here, this R would also be bigger than this P. Right? That means that we found an R in the gamma which is bigger than our P. So our gamma also satisfies the requirement for the cut, right? So that means that our gamma is a cut. Nice. So we prove that it's an upper bound and it's a cut. And that means that it's in the R. And so, yeah. And so now let's just suppose that there is some kind of thing that is less than gamma. And that means that there is S in the gamma, and this S is not in here, right? Right. Okay. And then since it's in here, it means it should be in some kind of an alpha. And then it means that this phi is less than some kind of an alpha. And it means that phi is not an upper bound of A. Okay, is that understandable? We were just like, okay, let some cut be less than our union. Then there is some element S that is inside, and S is obviously bigger than this, so it's not here. But it's also should be in some kind of a cut itself. So that means that this cut, which didn't include S, didn't include this cut, alpha. And so it means that it's not an actual upper bound because there is something that's bigger than it. Right? Is that understandable? I need to repeat again.
Okay.
Yeah, okay.
Okay, sure, great. So what we did just now, we were like, let's take a union, and it's a list upper bound, and we all like it, and it's a cut. So it has a nice property of having a list upper bound property. And it means we can use it later to do all kind of cool stuff that you can do with this upper bound property. What time is it?
9:30.
9:30.
9:10. No, 10 past 9.
Okay. I hope we can climb to at least 2 more steps.
What time are you leaving?
I should leave at like 9:50, I guess.
Okay.
So yeah. And I mean you're gonna have like free to live whenever you want, but like, because I know you guys have like your own stuff, but if alpha is in the R and B is in the R, then we just want to show that alpha plus B is also like in the R, right? And what is alpha plus B? Because these are the sets, right? What is the sum of the set? It would be,
Another set. That's all.
yeah, it would be another set,
Yeah.
but it would contain all the possible sums of all the possible elements here, right?
Oh, okay.
Okay?
So could we then say that alpha in the set alpha plus beta would be a cut?
Sorry? Can you say what?
The set alpha plus beta would alpha be a subset of alpha plus beta, right?
Yeah.
But if you were to define a cut within alpha plus beta, how would we do that?
Also, we're gonna prove that alpha plus beta is a cut,
Okay.
and then alpha and beta are a proper subset of it.
Okay.
Okay? Yeah.
Okay.
Okay, great. This is a great note. So basically, I guess Gaurav at this point figured out that what are we doing here with all those cuts and all those sets is very, very similar to the axioms I wrote to you before. You have a set like x and y, then x plus y is in the set, right? And so what we're gonna do is we're gonna take our like cuts and try to apply the same axioms to it. Why are we doing it? Because these cuts would help us to make an analogy with irrational numbers in the future. And then we're gonna be able to build irrational numbers upon those cuts. So that means that for now we have to prove the axiom of these cuts. Okay. And I know it looks tedious, but the thing is that like we have to go through tedious proofs because otherwise you would not have a basis in analysis. And if you will not be able to have a basis in analysis, you'll not be able to make rigorous proofs. So we have to go through this tedious work of like showing the basic stuff. Okay. So basically what we're gonna start with is an interesting set, and we're gonna call it 0 star. And it
There are stuff.
yeah, 0 star. And then would be a set of all negative rational numbers. Okay, so I hope it's clear it's a cut, but I don't want to go for it, it's a cut. But if you want to prove it's a cut, just take the properties of a cut. Like, I mean, if you can always like if I have some number -3, right? I can always take like -3 divided by 2, so I can always find something that's bigger than it, right? And so I can always go and approximate to 0, say. Okay, next. So we don't include 0 here. Okay, so basically, who can guess what are we going to do with the set? Okay, we're gonna go and be like 0 star plus alpha is a cut. So it's actually very like what we did with the rational number axioms before. We're just doing the same but for sets. This is why it's more interesting, because you actually see how you can apply this like intuitive axioms to something that's like more heavy than just numbers. Like say for example cuts. By the way, the cuts I believe are called Dedekind cuts. How do you spell the word today? I think I spelled it wrong.
D-E-D-K-I-N-D.
Huh?
D-E-D-E-K-I-N-D.
K-I-N-D. Dedekind. That's Dedekind cuts. And so basically this is something that all analysis students should know. So congratulations, you know what Dedekind cuts are. You are initiated into analysis students. Okay. So basically, what we're gonna do is try to prove why this actually works and why this is equals to this. So basically, this is our identity cut. Whatever you add to it, nothing much changes. Can you intuitively understand why? Because say you have a cut. Say your cut should be something like, it should be like square 3, but it doesn't have square 3, we don't define them, and it just goes to minus infinity, right? And then we have this cut that is not that doesn't have 0, right? And so the sum of cuts is defined as sum of all the elements inside, right? So basically, whenever you take a negative element and sum it up with this element, like say this A, you just make it less. Or it's like this small that it actually doesn't actually become less. You know what I mean? Because it tends to be a limit. So basically, this will be some like A minus some X. So this things plus this things would just throw them back a little bit to the left. But because they approximate 0, it wouldn't actually throw it too much to the left. So it still would be the same set. Okay? Okay, intuitively understandable. Do I need to prove it? Yes, I do. Believe me, this is like very hard. Like I always did it myself, and like going again like over it with somebody else is like tedious. But I believe in you guys. I invest my time in you. Okay, so first is we have to show that A plus B is a cut itself. A cut. Okay. Okay, so A plus B is non-empty. Great. And A plus B is totally not equal to the all rational numbers because, say for example, you take R that's not in the alpha and S that's not in the beta because R is just bigger than everything in the alpha and S is just bigger than everything in the beta. So R plus S is not actually in the alpha plus beta, right? But it's in the rational numbers. So yeah, we found something that's not in there, but it's here, and they're not equal. Okay, then second property. Okay, by the same definition, okay, so basically what we're doing here is we're gonna prove that A plus B equals to B plus alpha, but this is obvious because if you take an element R out of alpha, an element S out of beta, then R plus S is the same as S plus R, right? So yeah, it's the same. The third property, associative law, like Q plus S plus R is equals to Q plus S plus R. Okay, these are cuts. I'm sorry, I'm not using the Greek alphabet. So, can somebody show me how to prove this for the cuts? Will?
I'm good.
Okay, so we just be like, say Q is in the cut Q, and then S is in the cut S, and R is in the cut R, then Q plus S is in the cut Q plus S, and then Q plus S plus R is in the cut Q plus S plus R, right? And then you just do the same, but in a different order. You do like S plus R, and it's the cut S plus R, and then Q plus S plus R is in the cut Q plus S plus R. But this and this are the same because this is associative law for addition, and we already assumed it when we're doing the axioms. So that means that this are equal to each other, and that means that for any such Q, S, and R, they are always the same. And if all elements in two sets are the same, that means two sets are the same. So, yeah. I'm sorry, I have a very creepy writing. That it means that this set and this set are the same. Okay, next, associative law. Okay. Now I'm gonna ask you more questions because you guys seems like dying, and I know when you're dying, the best thing to heal people is like doing math. So. Okay. So if R is in the alpha and S is in the 0 star, then R plus S is less than R, and then means that R plus S are in the alpha by the property of alpha, because if something that's less than an element of alpha, it should be in alpha. Okay, yeah. So this means that the set alpha plus 0 is included in the set alpha. Why? In set theory, if you want to prove that A is in the set B, well, one way to go about it is to show that for any x that's in the A, it means that x is in the B. And then a common practice of proving that A is equal to B, actually there are two common practices. Okay, the first common practice is be like all of their elements are the same by some magical property that you somehow obtained before in your proof, but it's quite hard and quite rare. The more common way of going about it is like B is in the A and then A is in the B. Okay, and so if they're included in each other, that means that they're equal. And so whatever we're doing now, we went like alpha plus 0 star is in the alpha. Now we just have to prove that alpha is in the alpha plus 0 star, and we'll be done. Does anybody want to try to prove that? Okay. I mean, it's not quite obvious, but it's still simple. Okay, so let's pick any p out of alpha, and then pick r out of alpha, such that r is bigger than p. And then p minus r is in the 0 star, right? Because less, bigger, negative. Okay, and that would mean that p minus r plus r equal to p, obviously. And what it actually means is that this is in the 0 star, this is in the alpha, and this is in it, and this is in the alpha. Okay, and wait. What am I doing? Did I just? Yeah. What are you doing? Yeah. What are you doing with your life? You just proved that alpha is less than alpha plus 0 plus, but you already knew that. Sorry. 9:30. Why am I overproving stuff? Anyway, so the way we can go about it, I guess, is to prove that wait, how can I go about? Yes, actually, why do I even? Yeah, okay, no, sure. I did everything right. So we proved just two things. Okay, if you missed the way I did it, you can ask me if I repeat it twice, but I probably would do it wrong again. So yeah, better look in the chapter, because those things are quite obvious there. You'll be able to like do them yourselves, because it's just simple arithmetics and just like inclusions and sets. Okay, so and then Axiom 5 is actually like something interesting because it's a bit longer. Okay, so fix alpha in the R and let beta be the set of all p with the following property. There exists r bigger than 0 such that minus p minus r is not in the alpha. Okay, so what are we trying to do here is we're trying to find an inverse for the cut. And this is actually quite interesting because you'll have to somehow make up your own set and then it would just like ideally work as an inverse for the cut, and I think it's quite cool. Okay, so as we can see, if P would be some kind of a negative number, then this would be positive, this would be, yeah, and this would be positive minus negative, and if you make this somehow a bit bigger, this actually has a big chance of being positive, and actually a big chance of being bigger than everything in the alpha, so it actually may not lie in the alpha, right? So, okay, let's try this. So it basically means that there is some kind of a rational minus p, and it fails to live in the alpha, right? Okay, so basically what we're gonna do is be like, okay, if s is not in the alpha and p is equals to minus s minus 1, then p or minus p minus 1 is not in the alpha. Okay, why? Because because basically what we have is that s is not in the alpha, and then it would mean that this is actually, if you substitute it, is just minus s minus 1 minus 1. That means it's s plus 1 minus 1. It's just s. Okay, so basically what we're saying is like we found some way of tweaking s and writing s at p, and so this is not in the alpha, right? So basically what we're doing, we're trying to build an inverse, like, and it doesn't have to be minus 1. The minus 1 somehow considered to be a simple number in mathematics, so whenever you don't know what to write, just write minus 1. But I mean, the idea is this. Okay, and so it means that b would be in the b, because b is our set of inverses, right? Okay, so b is not empty. Yeah. Okay, a little remark. Sometimes you want to build some nice set with some nice property, and somehow this property like makes everything work, right? And you're like, oh my god, this is such a smart proof, I'm a genius, right? Okay, and when you do this, just calm down a bit and think if there is at least one element in your set. Because if you're coming up with some like magical ridiculous property, there's a big chance that there is no actually an element in your set. So yeah, just before you do this kind of things, think if is there at least one element in the set. That's nice. If not, then you'll have to prove there is at least one element in your set, and this may be quite hard. So yeah, don't do stupid things like Aya does. What time is it, by the way, guys? 9:30. Are you gonna go to the 10 p.m. shuttle bus? Okay, then you're watching our time. Okay, and this would mean that being not empty, if q is in the alpha, then minus q is not in the beta, and that means that b is not equals to q, because there's at least one element that's not in the b but in the q. Great. And then b satisfies the first property of a cut, not being empty, not being the rational number, also rational numbers. Okay, now let's pick some p out of beta, and then pick r bigger than 0, so that minus p minus r are not in the alpha. Okay, does this work? Okay, understandable. Good. Okay. Okay. If q is less than p, then minus q minus r bigger than minus p minus r, and then means that minus q minus r is also not in the alpha. Okay, what we just did was we showed that if q is less than p, then this is not in the alpha, and that means that q is in the beta. And if you remember the property of a cut, if there is something smaller than the element of a cut, it also should be in the cut. Okay? Okay. And okay, that means the statement 2 holds. I guess we just go with short statement and we just finish because everybody living, so they're gonna miss a big bunch of everything. But I hope you guys have a general like understanding of how do you like do those proofs in math, because some of them are quite easy, but also they're intuitive, and also they build the entire math field, so you want to like know how to do them because it's some kind of a ritual. You just have to go over it. Okay. Then what we do, we put a second statement, and now let's t be equal to p plus r divided by 2. And we remember we just picked some r that's bigger than 0. Okay, and then t is bigger than p, obviously, and then minus t minus r2 is equals to minus p minus r is not in the alpha. That means that t is in the beta. Why? Because what we just did is that we somehow made some artificial t, and we found some artificial r, such that this equals to this, and we know that this is not in the alpha, right? So we just made up some artificial t, but it worked, and it's bigger than our p, and that means that we are always would be able to make up a t that would be bigger than p, and it would exist in our cut. Do I need to repeat it again?
Yeah, somehow.
Yes, it is. Okay, so basically we had a cut, some kind of cut, and we had, and we're just picking any random p. Remember, by the third property of a cut, we need to make sure that there are always some other thing that's bigger than p, and it's also in the cut, right? Because we want the cut to approximate to here. So we just built some artificial t, and it wasn't actually very hard, right? We just did this, and it worked, right? And so we found it. So, and we found t, we found r for it, and so that means that this property holds. It's not in the alpha, and it's not in the alpha, by definition it's in the beta, right? Okay, great. And so it basically means that we were able to make b a cut, and it has a specific property. Now what we're gonna do is that we're gonna show that, let's take some kind of an r out of alpha and s out of beta, and then minus s that's not in the alpha. Okay, and then r is less than minus s, and r plus s is less than 0. Okay, and that means that alpha plus beta is in the 0. Okay, interesting. Basically what we're doing here is we're like this in the set of b, thus what we have is we have this. It's not in the alpha, and because it's not in the alpha, it certainly is bigger than any of the elements of alpha, and then we just go put it here, and it's less than 0, so it's in our 0 star set. And there was initially a sum, right? So we just put that the sum is in our 0 star set, right? So what do we have to do now? Like, what is our grand plan? Why do we need this? What do we want to do with it in the future?
To prove that one, the first one, alpha plus beta is an element of r.
Okay, so you say alpha plus beta is in the R? Wait, we proved it. We proved it, right?
Oh,
yeah,
okay, okay.
we proved that it's cut.
Okay.
Okay, but we build beta as an inverse of alpha, right? So we would want it to be ideally that alpha plus beta just equals to 0 star, right? We want this. And so far we have this. What do we lack?
Prove it the other way.
Yeah, we just need to make it alpha plus beta has 0 star. Because if this and this holds, we'll be able to prove this. Okay? Okay. So yeah, let's just do that.
And just to keep track of, this whole proof is proving this is for rational numbers.
Oh, okay. So we had a rational number system,
Yeah.
and we built cuts.
Yeah.
And those cuts approximate irrational numbers.
Yeah. Okay.
And so when we're gonna build the whole cut system with all the axioms, we're gonna be taking the supremum of it and defining it as a rational number. Great, we build a rational number.
Okay, so that's what we're doing.
Yes. Are you okay? You have like a.
Yeah. My voice.
I mean, you have a very sexy voice now, but like I think it's. Being sick to attract girls is not a good way to go about it. Okay. Now what are we doing now? Yes. Okay. So we basically wanna. Okay. So let's pick V out of Z star, and then W is equals to minus V divided by 2. Okay, we'll just make it random. Then W is bigger than 0. Why? Because this is negative and this is positive. And there is integer n such that nW is in the alpha, but n plus 1 W is not in the alpha. And if you think this is a hard step, just remember that alpha is a cut, and everything that's like in like less than it is inside, and everything that's bigger than it is outside, right? So basically, if this is some kind of a positive number here, say W, and we just like go and jump at the wheel. 2W, 3W, 4W, oops, 5W. Okay, so this means that we'll actually, at least after some jump, we'll be able to find n, in this point is like equals to 4, such that this is in the alpha, but this is not. By the way, this property is called Archimedean property. Okay, and the thing about Archimedean property is what Archimedes basically said is, imagine you have, okay, I'm not a historian in this, so I'm not sure he said exactly this, but as far as I remember reading in some kind of journal, it was if you have two intervals, the property of the intervals is that building the smaller one like next to each other like this, at some point it would overgrow this interval, right? So basically what he is arguing about is that there are no infinitesimally smaller intervals in this one. So like, even if it's like very small, at some point you'll overgrow it, right? And this is Archimedean property. And our side has it. I think there actually are sides that don't have it, but you have to dig deeper into it. I didn't do it yet. Yet is a good word here. Okay, and so what it means is that if we'll just go and be like P equals to minus n plus 2W, which is making it up, then P is in the B, since minus P minus W is not in the alpha. Why? Because minus P is just n plus 2W, minus W is n plus 1W. We already said it's not in the alpha, so good for us. And then, yeah, okay. And then it means that V is NW plus P, right? And I guess we can see why, because this is minus n plus 2W, this will be minus 2W, okay? So V is minus 2W, and we initially defined W as being minus V divided by 2, right? So basically, I know it's a lot of variables, and it's just like playing with it randomly, but this is what you're doing. Like, the proof is not that hard. So basically, you just pick a constant that you like, you pick your favorite name for your variable, and you go and do just like things like that. Because intuitively, what you're trying to do is being like, we are able to somehow put things like this. So we were able to find two sums that would actually lie in the set of negative integers. And once we'll build those sums, that would mean that 0 star is in the alpha plus beta. Right. So what we're doing now, you can actually go and do your own proof. It may not look like this, because this is just like some play with arithmetics. What you need to do is just like to somehow construct a sum, like all kind of sums from here, using just you can choose everything from here and everything from here. And in theory, this is understandable. So you'll be able to just transform it in variables, and you're good. Okay, and this would mean that this is in the alpha plus beta, and yeah, and that's we finish the proof. Thus we just build such that this works. Because basically what we did is we'd take any v from here, build some kind of stuff, v is in here. Okay? So basically what we did was just like take any v tends to be here. That means for any element in this set, it's always in this set. That means this set is included in this set. And what's inside is important if you want to be rigorous, but it's not as important to care much about it. Like, this is the kind of proof you'll be able to do on yourself, especially if you like go and try. And I really think that we should meet at once, not for a lecture, but for you just actually just sitting together and just doing exercises. Because otherwise, like, you'll become used to like listening to lectures, but not actually like doing your own stuff. And doing your own stuff is important. Okay, so conclusion. Alpha plus beta equals 0 star. Great! That means we were able to find b such that it's an inverse of alpha. Inverse exists. We're good. Thank you for today.